the remainder theorem and rational root theorem. In this video, we'll show how these theorems can help us sketch a polynomial function by hand. Consider a polynomial function. We could type this into a graphing calculator or desmos.com, and we could get the graph that looks like this. The important things that we want to keep in mind with polynomial functions are end behavior and the number, the value, and the multiplicity of the real roots, that is, where the graph goes through the x-axis. The question that we'll be asking and answering today is, are there any rational roots, and what are the possible rational roots? So first, let's review the remainder theorem. Remember that the synthetic division process will give us a remainder. The remainder tells the value of the function at that input value. If the remainder that results from dividing a function by n is 0, then the value of the function at n is 0, therefore n is a root. Identifying the zeros or roots is a very important step in sketching the graph of a function by hand. So pretend that for the given function we had no access to a graphing calculator. This was the function that we did graph a moment ago. And the question we could ask ourselves is, -1 a zero of the function? We could use synthetic division. So we'll refresh your memory on how to synthetically divide. We take the coefficients of the terms, and if there's any missing x terms, remember we use zero placeholders. In this case, there's no missing x terms. We're dividing by -1, which goes on the outside. We bring the 2 straight down, and we multiply it by the divisor, and then we add to -1. -3 times -1 is 3, which gets added to the -24, and we continue like this. And we're interested in the remainder. 6 times -1 is -6. We have a remainder of -36. Therefore, the value of the function at x equals -1 is -36. And so -1 is not a root of the function. We also could have figured that out by substituting -1 in place of x in the function. So then we try other numbers to determine, is there another root? Here's the same function. Is 2 a zero or a root of the function? We go through the same process of synthetic division, looking at the remainder. According to the remainder theorem, 2 is not a root of the function. And again, we could have also determined that by evaluating the function at x equals 2. So the question that we have is, we've tried 2 numbers to determine if they were roots. We tried -1 and we tried 2. Neither of those worked. Are there any rational roots, and how do we find them? So it turns out something called the rational root theorem will help us find the possible rational roots. Again, here's the function. We're going to consider p over q, where p are the factors of the constant term, in this case -30. Q are the factors of the leading coefficient, in this case 2. We write all of the possible rational roots of f of x by looking at the p, which is the factors of the constant term, and q, the factors of the leading coefficient. Then we look at p over q, and we list all of the possible values of p over q. I typically try to do this in an organized way. I take all of the values of p and write it over plus or minus 1 first, and then all of the values of p over plus or minus 2. Remembering that we already know -1 and 2 are not roots. But I tried to divide by 1, and I did get a remainder of 0. Now 1 is always a nice number to try to divide by because it's pretty easy to do synthetic division. I know, according to remainder theorem, that 1 is now a root of this function. Therefore, the original function can be factored where x minus 1 is one of the factors, and the remaining factor comes from the bottom line of your synthetic division. The 2 is the coefficient of x to the fourth plus 1x cubed minus 23x squared minus 10x plus 30. So we know how to interpret the remainder theorem. We now have a way of determining all of the possible rational roots. And at this point, we have basically another polynomial function that we want to consider the p over q. Turns out there'll be the same possible rational roots, and maybe we'll try 1 again and see if 1 is a double root. And turns out 1 is again a root, so we say that it has multiplicity 2. Therefore, that polynomial that we divided by x minus 1 can be factored like this. So now what we want to do is look at that cubic and try to find the possible rational roots of it. We could try to divide by 1 again, but this time we see that 1 is a root of the function multiplicity 2, not 3, so 1 doesn't work. So we're going to try something else. We'll try to divide by negative 1. We actually knew earlier that negative 1 was not a root, and this just kind of reinforces that. The value of the curve at negative 1 is negative 8. So we can try something else. We can try negative 2. We know the value of the curve at negative 2 is positive 6. So between negative 1 and negative 2, the curve has hit the x-axis. So we can try a root of negative 1.5. Once again, we know that 1 is a root of the function with multiplicity 2. We're trying negative 1.5. We do get a remainder of 0, telling us negative 1.5 is indeed a root of this function. So we can write the function in factored form this way. And I see that I have one last quadratic expression that we could figure out what are the roots of that. And so just to summarize, these are the roots that we have so far. So we could write our function this way. We're now going to take a look at that quadratic expression and using the zero product property, set it equal to 0. And we find out that x equals plus or minus the square root of 10 are also roots of this function. These are irrational roots. So at this point, because the function is to the 5th degree, and we have our 5 roots, 1, 1, negative 1.5, square root of 10, and negative square root of 10, we can take a number line and we can show those roots. We can think about the end behavior. Because the original function is raised to an odd degree, it's going to be increasing towards the right end, and the left end will be the opposite, decreasing. And it's going to go through that root. Remember, 1 is a double root, so it will hit it and then come back down. And there we have shown you how the remainder theorem, the rational root theorem, coupled with synthetic division, helps us sketch a polynomial function by hand.